In this lesson, we're going to learn about parabolas and circles. So for the next few lessons, we will be exploring a class of equations called the conic sections. The graphs of these equations form the familiar shapes of circles, parabolas, ellipses, and hyperbolas. We start by looking at each one individually, and then lastly we'll explore how they all relate as a group. The first conic section we explore is the circle, but for most of you this will be a review, so we'll not spend a lot of time on them. After that we'll look into the parabola in detail. Circles defined geometrically. A circle is the set of points in a plane that are equidistant from a central location. We give the coordinates hk as the location of the center of that circle, and define r to be the constant distance, which is known as the radius. And you may or may not have heard of a circle defined in that way, but if you see it visually, it really does make sense as to why it is the way it is. So I'll show you real quick the thought process behind it. So if I have a center point, which is C, and then R is my defining the radius between the circle itself that's going to be drawn and C, and then P is just some point on the circle. So if you notice, the distance between C and the point on the circle is 4 units. Now if I keep that distance constant and rotate point P around 360 degrees, we get the shape of the circle. So this is all the points that are the same distance away from point C. You know, if we change the radius or change where the center is located, this same result occurs. We just might have a larger circle or a smaller circle respectively, but the radius stays the same. That's what creates the shape of the circle. Now, developing a formula for a circle, we take the general situation, center point at hk, and xy as just some point on the circle. We know that we're keeping the distance between the center and that point xy constant. We're calling that the radius. So using the distance formula, we could say that r is equal to the square root of x minus h quantity squared. So we take the difference of the x1, x2, plus y minus k quantity squared. Or instead of expressing it this way, generally the standard equation for a circle is written as x minus h quantity squared plus y minus k quantity squared equals r squared. And there's the general form of a circle. Now, let's move on to parabolas. A parabola is defined as the set of points in a plane that are equidistant from a line and a focal point. So now we're not just looking at equidistant points from a single central value, we're looking at the constant distances between a point and a line. The line is called the directrix, and the point is called the focus. And just like with the circles, let's take a look at an applet to kind of help us understand, how this definition works and where the shape of the parabola comes from. So here I have a point that is a focus, and I have my directrix. So there's the point and the line. And what this definition says is the parabola is all the points P, so here's my point P, that are equidistant from the focus and the directrix. So if you'll notice, I have point C right here, and that's basically the minimum distance between P and the directrix. So the line that is at a right angle to the directrix is going to be the one that's the shortest distance. So the distance from P to the line is 5 units, and the distance from P to the focus is 5 units. Now that distance isn't going to be constant. If I move, if I move point C, which in effect is changing the location of P, the distances between the focus and point P and the directrix is changing, but it always stays the exact same value. So no matter where I stop on this parabola, I have that distance is constant. And if you'll notice, as I move that point, I end up with the shape that you may recognize as a parabola. Now, let's try some other values for the directrix and for the location of the focus. So let me tilt the directrix and let me move the focus closer to the directrix. And we'll erase what we have, and now I'll draw all the points that are equidistant. So now you might see that parabolic shape a little bit better. So it doesn't matter how it's tilted, you will always have the parabolic shape as long as you're finding the point that is equidistant between the focus and the directrix. Now, developing a formula for a parabola is a little bit more involved than developing one for a circle. But we're going to do it because I think it is instructive. So basically what I have here, I have the directrix, and I have my focal point right here. Now, those two objects, every single point on the parabola is going to be at equal distances between the focal point and the directrix. So what I need to do then is I'm going to define these two distances. I'll call this distance 1 and distance 2. And one thing we know about that is they are equal. We just showed in the construction applet that those two distances are equal. And we know how to calculate distances between points, but what we're going to need are locations of where these points are found. So the point on the parabola is easy. I can just call it xy. So all the points that exist on the parabola. But I'm going to need to be a little bit more specific for the points on the directrix and where the focus lie. Now, there is one location right here where the distance from the vertex, and this point right here is my vertex, from the vertex to the focus and from the vertex to the directrix, that's equal. And there's only one point where that occurs. So that's a special distance, and we call it P. And it turns out that P is an important number when it comes to creating our formula. So it's a good starting point. Now, I'm going to give coordinates to the focus based off of that. The vertex, I will say, is located at 0, 0. I can locate it at HK, but for our purposes, in order to derive this formula, it's going to be easier for us to assume the vertex is at 0, 0, and then use shifts and translations in order to move it later on. So that means the focus is at 0, P. Okay. Then the directrix is going to be the line not x equals, this is a horizontal line, so it's y equals negative P. And the next thing that I know is this point right here on the directrix. that point right there is a distance over x, and it's on the directrix, so its y value is still negative p. So that locates all my points that I need to work with. So d1 is the distance from the focus point to xy. So I'm going to write that as x minus 0 quantity squared plus y minus p quantity squared. So the focus is at 0p. That point on the parabola is xy. I'm just calculating the distance between those two. d2 is the distance from xy down to that point on the directrix. So it's going to be x minus x quantity squared plus y minus negative p quantity squared. And I have some things that I can work with and reduce. Let's see what happens. So in the next line, what I can do is first note that x minus 0 squared is just x squared. Y minus p quantity squared could be written as y squared minus 2yp plus p squared. And that's going to be equal to, well, x minus x is 0. Any 0 squared is just 0. Y minus negative p is just y plus p. So this is going to be y squared plus 2yp plus p squared. Now, I'm going to square both sides, because if I have the square root taken on both sides, I can square both sides and just kind of release what's underneath those square roots, which gives me x squared plus y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. And there's a bunch of terms on each side that are equal. So if I subtract p squared from both sides, they're going to cancel on each side. If I subtract y squared from both sides, they're going to cancel. Now, the 2yp's will not cancel because they're opposite in sign. So let's say I add 2yp to both sides. Then I end up with canceling it here, and I get x squared equals 4yp. Sorry, I wrote 2, but it's 4yp. Now, what I can do next is, in order to locate this instead at put the center at hk instead of at 0, 0. Then it works out that I can just use translations, and it's going to be x minus h quantity squared equals 4p times y minus k. That is the general form of a parabola. And in particular, this is a parabola that's going to open up or down. If you want it to open left or right, it would be y minus k quantity squared equals 4p times x minus h. And that's perfectly fine. You can have a parabola opening left or right. Now, this equation that I've just developed this is basically the same thing y equals a times x minus h quantity squared plus k, which is the vertex form of a parabola that you've seen in the past. So basically, if you subtract k from both sides, you get y minus k equals a times x minus h quantity squared. And if you divide both sides by a, 1 over a times y minus k equals x minus h quantity squared. So essentially it's the exact same thing where 4 times p is equal to 1 over a. So these constants that tell you like how wide the parabola is, there's just a different way of expressing them. Now, what's nice about the form we have it as is with the 4 times p is that the value p is used in locating the focus and the directrix, if you know where the vertex is, that is. So that's helpful. Another thing is you can tell how wide the parabola is by using this line right here. The line that is parallel to the directrix and passing through the focus. This is called the latus rectum. And I'll give you a moment to giggle, and when you're done, we'll come back to the mathematics. All right, you good? Okay, so it's called the latus rectum, and it is the distance between the 2 points that are, on each side of the focus parallel to the directrix. So what's nice about that is that distance is 4 times p, so this number exactly. So if you have that number handy and you know where the focus is, it's very easy to graph how wide your parabola is supposed to be. And that is very helpful to get a good, accurate picture. So the equation of a parabola in standard form will look like x minus h quantity squared equals 4p times y minus k if it opens up or down. Y minus k quantity squared equals 4p times x minus h if it opens left or right. So what I generally think about here is the variable that is not squared is telling you the direction of it. So the y variable is the y-axis, so up or down. The x variable is the horizontal, so left or right. So the variable that's not squared. As we said, it's very similar to the original vertex form of a parabola. But some things you want to remember. HK is always the location of the vertex. So if you have that point, that's a great place to start. P is the distance from the vertex to the focus and to the directrix. So if you have that number, that's very handy in graphing. 4 times p is the width of the parabola through the focus. If p is greater than 0, the parabola is either going to open up or right. Both of these are the positive directions. So if p is positive, it opens to the positive direction. If p is negative, the parabola opens in the negative direction. All right, let's work some examples. So find the vertex, focus, directrix, and axis for the following parabolic equation. Then provide a sketch and determine its domain and range. Okay, so the first thing that I look for is whether this parabola is opening up or down or left or right. So the variable that is not squared is the vertical variable. So it's going to go up or down. And I'm not saying which one it is just yet, but that's my first thing that I look for. All right, we're going to need the vertex. The vertex is relatively easy to develop. It's just the coordinates, in this case, -3, +1. The directrix and the focus, in order to come up with those, we're going to need to know the value of p. So from my formula, 4 times p is equal to -4. So p is equal to -1. So first off, what this means is my parabola is pointing in the negative direction, so it's going to be pointing downward because p is negative. And the distance from the vertex to the focus is 1 unit. And what I'm going to do is go ahead and plot some things. So the vertex is at -3, 1. So right there is my vertex. the parabola is opening downward, and P is equal to, let me say the absolute value of P is 1. So 1 unit above and 1 unit below is where we're going to find the directrix and the focus. So the directrix is going to be this horizontal line right here. And this is going to be my focus. Now, to determine, what's happening with the parabola, outside of those points, the length of the latus rectum is going to be 4 units. So 2 units on each side. All right. That shows me how wide this parabola is going to open up. And I can use that to get a pretty decent sketch of my parabola at this point. So I know how wide it is. I know that the direction that it's opening, where the focus and the directrix are, all of that stuff. I haven't labeled where these things are, but it's just fine to go ahead and start labeling those. See, the textbook often gives you a set of formulas for everything, but for me, all the different formulas make my head swim. What I do instead is I know basic facts of, how the vertex, the focus, the directrix all interact with each other. Then I use that with a drawing to try and help make sense of where they're located.